Now I'm gonna be explaining another important article about zero-shot learning, again for a task of entity linking, but this time we use knowledge graph and enhance it using knowledge graphs. So we focus on this paper in 2021, and the motivation is that the entity linking is a fundamental task. Use of knowledge graphs is a fundamental task for a successful use of knowledge graphs in many information systems, and it maps textual mentions to their corresponding entities in a given knowledge graph. However, with the rapid evolution of knowledge graphs, a large number of entities is continuously added over time. Performing entity linking or new or unseen entities poses a great challenge, as standard entity linking approaches require large amounts of labeled data for all new entities, and the underlying model must be regularly updated. So, to address this challenge, several zero-shot entity linking approaches have been proposed, which don't require additional labeled data to perform entity linking over unseen entities and new domains. Most of these approaches use large language models such as BERT to encode the textual description of dimensions and entities in a common embedding space, which allows linking mentions to unseen entities. While such approaches have shown a good performance, one big drawback is that they are not able to exploit entity symbolic information from the knowledge graph, such as entity types, relations, popularity scores, and graph embeddings. So in this paper, a knowledge graph enhanced zero-shot entity linking approach, which extends an existing BERT-based zero-shot linking approach with mention and entity auxiliary information, is explained. This is the architecture that, although we use mention in context, but we can also use it separately and then aggregate these to result to have a better mention embedding. The same thing for entity embedding, because not only your entity is important, not only the entity description is important, but also the entity, by itself is also important, that we can aggregate these two to have a better entity embedding. And the rest of that is standard because we use the entity embedding and mention embedding to get the score. So they extend the candidate generation and candidate ranking modules, and then they extend the by-encoder architecture by infusing auxiliary mention and auxiliary entity vectors. This model is used to generate candidate entities for a given text mention. Second, we extend the cross-encoder architecture by infusing symbolic knowledge represented as an entity graph vector, such as entity types, entity popularity scores, and entity embeddings. This module is used to rank the entity candidates extracted in the previous module. So the mention context and entity descriptions are encoded using two BERT transformers. These are transformers, and we use this reducer as a kind of pooling mechanism because you have many tokens, so we should reduce to just one vector. The same thing for entity description and this mention concept. So we represent them, but now to be able to aggregate mention and entity auxiliary vectors, now we have auxiliary information, so why not using them and aggregate them? So the same thing, we can use this 10H nonlinearity for that. After that, we aggregate the mention context and the mention auxiliary. We aggregate them for mention and entity, And finally, the dot product gives the corresponding, we get the score. For mention I and entity J, we have this score. And then we have a batch that it has B pairs. For each training pair, the loss is computed because we want to maximize this one, this score. We want to maximize the score of mention I with entity I. The knowledge graph enhanced cross-encoder is shown in this figure, that now you also have the information from the knowledge graph, because you have a graph and then you also aggregate these informations. So it's shown, and there are three inputs. First, the mention context which we have talked about for an input mention I, and then the entity description for an input entity EJ, and finally we have this auxiliary entity vector. The auxiliary entity vector is a numerical vector extracted from a source knowledge graph for the entity E sub j. And the mention context and entity descriptions are concatenated and encoded using a BERT transformer. So we have a single vector which we give it to the transformer, and then we reduce it, a kind of pooling mechanism, and finally we get those representations. Once a transform vector is calculated, we use an aggregation function to aggregate this encoded mention context and this entity description and the corresponding auxiliary version of that. And then to aggregate the vectors, we use a simple concatenation, and the score of each mention M sub I and entity E sub j is calculated like this. The network is now trained using the softmax loss to maximize this score for the correct entity given a set of top K entity candidates.